started. In this lesson, we shall focus on linear algebra. As obviously we know very well that we are focusing on the module MAM2000 W2LA linear algebra. So this is the sort of module that we shall focus on today. It's a very interesting one. Let's actually look at a wide range of problems as we begin. Right, first things first, we look at question one. And question one is actually, once again, on similar stuff, which we looked at previously. And once again, we shall be moving back and forth, between sets of questions and past exam questions. As we attempt.
Which paper is this?
That's a good question. This one is 2022. Okay. Yeah, but yeah.
Did we finish? But we did finish that one. I wanted to.
Yes.
I wanted to see how you approach certain proofs.
Yeah, that's fine. I'm still gonna do those proofs. Okay, I'm still gonna do those proofs. Okay. Yeah, I'm still gonna do them because those proofs are here in this paper as well. They normally put them at the end of the paper, you know. I realize.
Yeah, because with these questions, I don't really struggle. I can do them on my own and then ask where I don't really understand.
Yes.
So I just wanted us to, do proofs a lot because that's what I struggle with.
That's fine. That's fine. We shall spend a lot of time on the proofs. Okay. We shall spend ample time.
Okay, no problem.
Yeah, I've actually, in particular, I just decided that we shall obviously, allocate much time to actually focus on the proofs. All right.
Yeah.
Okay, good. We still have time, but obviously, the plan is to discuss every single day.
Okay.
I'm sure, therefore, that our time will sort of balance up. If need be, we can even, on some days during the week, discuss in the morning and discuss in the evening, something like that. With me, just to make sure that we sharpen our skills better. Okay. And that is victory. Victory is most certainly assured here. Right. So obviously I know that some of these are pretty straightforward. We have a perfect chance to just exercise ourselves, our minds, and make sure that we brush up, we polish up. Okay. Right. The easy ones we shall quickly, just the solutions and just move on. Right.
Okay.
I was obviously looking at the rest of the papers. Like, look at the matrix A and the matrix U are given, and the matrix U is a row echelon form of the matrix A. You need not check this. Okay, that's obviously examiner row reduced it to the row echelon form, and now they're saying give the rank and the nullity of the matrix A. Let us take a look. First things first, we shall focus on the rank of the matrix A. Right, and the rank of the matrix A, we realized last time, is the number of the non-zero rows, and we have 1, 2, 3 of them, and therefore it is therefore very obvious that the rank is 3, correct? Right, so as said, I know that some of these you find very straightforward. Next, when we find the nullity, we will remember that the rank. Right, so some of this is much of a repeat. It's very similar to what we saw in the 2023 paper. Right. Right. So plus the nullity. So the rank of A plus the nullity of A will be equal to the number of the columns, which is 2, 4, 5, for example.
5,
right. If the rank, and we see there 1, 2, 3 non-zero rows plus the nullity of A, which equals 5, then this means that the nullity
is 2
of A equals 2. Right. So you shall come here and put the nullity as 2. So obviously that is, I agree with you, very easy. And okay, the structure is maintained.
Yeah.
I want us to just move and recap on some of the things. The null space of the matrix A, and obviously the notion of the column space, we just recap on that one. And now, what is the null space of the matrix A? Right. So there are a couple of things, obviously, to take into account in terms of what we mean by the null space. Now, the null space of the matrix A, by definition, the null space is the matrix A plus multiplied by a column vector, which is of the right size, and this equals the zero vector. And with this kind of multiplication, we actually are able to get the actual null space there. So obviously the matrix A has already been row reduced for us, right? And since the matrix A has already been row reduced for us, we have a perfect chance to see exactly what we have here as the null space of A, right? So if you look very, very carefully, what are we able to see exactly here? Okay, let me first take note of the following. That what you have here is, in general, to write the null space, we proceed as follows. Okay, but first yeah, let me just write it like this. Right, you'd have that the matrix A itself can be written minus 402. Just want to write this, and 0 minus 1, 3 minus 1. Just writing the matrix A. This is an idea I want to bring across here as we discussed the notion of the null space. We have 3 minus 6, 3, 6. We have minus 1, 2, 1, 0. Okay, this is the matrix A. And you then say 2, 4, 5. So you'd have here, you can write x1, x2, x3, x4, x5, sort of as the appropriate column vector, and this would be equal to the 0 vector. Okay, so if this one here is 2, 4, is 4 by 5, 2, 4, 5, and this one is 5 by 1. Right, so if we multiply these here, what will the size of this is? It's going to be 4 by 1. Right, so
4 by 1.
Yes, it's going to be 4 by 1. Thank you so much. So this is going to be exactly 4 by 1. Okay, so with this then, we're able to write the equation that will actually yield the null space for us. Right, so, and obviously we're interested in then saying we're interested in the null space. But the examiner was very kind to us to have actually performed the row reduction, and which means that if we row reduce this one here, it's going to reduce to this. So it's going to reduce to the 3 zeros, and 0 minus 1, 0, 1, 2, 0, 3, 0, 3, 0, minus 1, 0, 1, 0. And then here we have here exactly x1, x2, x3, x4, x5, like this. And this is, so yeah, this is sort of what we're going to have here. Okay, so if we row reduce these, it will actually, take us to that point there. And so the null space would have to be, therefore, a vector of this size. Okay, it would have to be the solution to this particular equation, matrix equation. So the solution to this particular matrix equation, it can be obtained here. So the question is, if this matrix equation has been written, what is the solution to it? Okay, so the solution to this is obtained by multiplying these two matrices and attempting to therefore find the actual values of the x1, x2, etc. Right, so at this point, what would the answer be exactly to this? So let us investigate together. We are actually, so you would multiply these by that. Okay, and then obviously we'll have the bottom one. So you'd have that 2x1 for the first equation, 2x1, and then there's going to be an x2. There's going to be a 3x, yeah, x2 here, and okay, there's going to be an x3. Okay, just to, okay, because this is 0. Yeah, we're just gonna jump 1. So x2 is gonna be actually 0, and then now you're gonna be having 1 x3, which is just gonna be x3, and then there's gonna be an x4, which is 3x4, and there's gonna be what? There's gonna be minus x5, and the result is 0. Right. So, and let me write it on the next slide as follows. Right, so what you're then going to have, by just looking at this matrix and imagining that you're going to have x1, x2, just want to summarize it here. x3, x4, then
Okay.
x5. Right. So, and obviously these being equal to the fourth, like this. You then have 2x1. X2 is going to be started with 0. Then there's going to be an x3. There's going to be 3x4. There's going to be minus x5. The result is naught. Next. Right. So that is multiplying. Yeah, the second row is going to be minus x2. 2x3 is 0. Okay. So that is what you can have as a consequence. Right. So what else then are you going to have? Okay, right. And yeah, and the pattern continues. But I want to make mention of something very important here. That key to this is the fact that is there any row reduction that is possible to these here? Well, it is certainly possible, right? So, I mean, that would simplify the work as well, because it doesn't really matter what you do. Okay, but you still can continue with this. It's the same thing. So that is the second one. The third one is going to be 3x what? 3x4?
3x4.
Together with x5. Okay, but once again, one student can just, you know, complete the reduction process to the most reduced, but yeah, doesn't really matter. Okay, and then what is the last one? The last one is going to be exactly x5. Okay, now sometimes you can write x5 equals x5, but you can give it the name t. Okay, something like this. Okay, and obviously where the t itself is a real number. At this point, you must therefore be in a position to solve them backwards. So if x5 is known, then we have x4. What is x4? It's minus x5 out of 3.
T.
Yes, you can call it minus t out of 3. Okay. Then what about x2? X2 becomes what? Becomes minus, it becomes 2x3. Okay, yeah, because it becomes minus 2x3, but negative cancels out. Okay, right. And so what then is x3 here? All right, so you continue and write the next thing. So let's solve here for x1. Right, so as said right now, there's just that repeat in the pattern. Right, so if you solve for x1 out of this, you'd have 1/2 minus x3 minus 3x4 plus x5, like this. Okay, so what then are we able to get out of these here? Right, and we can look at this and think, right, we can get solutions out of this. And in the end, then, if we get the solutions out of these, and there are many other solutions we can achieve. But what is then the simplest way? Like I was actually suggesting, the simplest way is, as much as this is okay, but the simplest way is the following. Okay, let us take the 2, 0, because I don't want the redundant things. Okay, I don't want the redundant variables there. Because they're just going to waste our time, and they're going to, you know, make us have to simplify the equation, substitute into the other, and so on. Now, one thing that it's easier to do is to just make sure that this is in reduced row echelon form. Right, so at this point, obviously, this is okay. This column is okay. Right, so this column is fine. You just have to row reduce this one here. And with that, then you're going to say row 1 minus row what? Minus row 3. Right, and then with that, it's going to be 2, 0, 1, and then it's going to be 0. And then this is going to be minus 4, 0, minus 1, 2, 0, 0, 0, 0, 0, 3, 1, 0, 0, 0, 0, 0. Right, so in the end, then, what do you have? What do you have? Okay, let's check. Now, this one now, obviously you can see that there is a pivot here and another pivot here. It's okay, you can make it +1. And then obviously now we're able to see another pivot here. We can keep it as 3 like that. And now also there's something we can do. Let us check. If this is the case, can we be in a position to achieve, because there's no pivot here that can produce, that can actually make this a 0. Now, because of that, then we pretty much are good. Okay, I wanted to make sure that this is pretty better simplified to avoid just redundant equations. Right, so that with this in mind, then we write 2x1 together with x3, and then minus 4x5 equals 0, because this is x1, x2, x3, x4, x5. Okay, so let's write the next one. It's going to be minus x2. 2x3 is naught. And then you have 3x4 together with x5 equals 0. And then once again, we said that x5 can be called x5, but you can call it t. Right. So with this, then we are able to, we just need to write the column vectors as in the right manner. So from this other equation, we're able to get that x4 is minus t out of 3 from this one. Okay, minus t out of 3, for example. So that's okay. Next, let's find x2. Right, we can find x2 or we can find x3. We spoiled for choice, so we have the freedom to get whatever we want. But what do we want? We can actually be able to get x2. x2 is nice. Okay, you'll see why. x2 is going to be 2x3. Okay, it's just a whole number there. If you take it to the other side, then it's going to be negative, and then you're going to have obviously positive there. Next. Let's look at this one. x1 is going to be 1/2 out of this. Then you have minus x3 plus 4x5, like this. Okay.
Is it not true now?
Please come again. Yeah,
is it not 2x5?
It's 2x1, so we divide it by 2.
Yeah, 2x5 instead of 4x5.
Oh, yes, you can erase multiply out so that it becomes minus half x3 plus 2x5. Correct. Yeah, that's fine. So let's write the equations on the next slide. Right. So what is the first equation? x1, the one you just mentioned. Thank you so much. Is minus half x3, for example. So you can write that one. So you can write minus, minus 1/2 x3. Okay, I'm just copying this one. Is minus 1/2 x3 plus what? 2x5. Okay. Then
plus
2x5. Then what is the next one? The next one we said you can write x2. x2 is 2x3. Then what about x3? Okay, then we have yeah, we can make it obviously S. Yeah, S. We can make it S. Okay, I want to write the ones that are present first. Let me see what we have. Right, so let us write those that are present so that you can see which variables are free. Right, so now dealing with the pivots, we wrote x2, then we have also what? We have x4. We wrote x4 equals minus t out of 3. x4 minus t out of 3. What else do we have? x5. Right, yes, we have x5 equals t. Equals t. Right, so we're able to see this, but what is the meaning of all these here? Right, with this in mind, we're able to see therefore that we need to call, we have x3 as well, we'll call it S. Right, so let x3 be S. And that means x1 is minus half S2 t. x5. x5 is t. x2 is
Yes.
2s. x3 is s. x4 minus t out of 3.
Yes.
x5, it's exactly a t. Okay, we're good. Now, what is the meaning of all these? Well, the meaning of all these is that x1, x2, x3, x4, x5 together, they're able to produce let's deal with the s's first. Right, so dealing with the s's first, there's minus half s, 2s, s, 0, 0. 2t, 0, 0. Minus t out of 3, t. Okay, let's check this. So, yeah, we've just done some grouping of the s's. So the s's are together and the t's are together. Okay, let's take a look at this and see what this is going to produce for us. So now it means, therefore, you're going to have x1, x2, x3, x4, x5. All right. So now normally we can factor out the we need to factor out the variable s, of course, but also the fractions, we can take them out. So at this point, you can take out s over 2. Okay, let us take out s over 2 from this one. Right, let's take out s over 2 from this one. So if you take out s over 2, then it's minus 1. Okay, so this one here is going to be what? It's going to be a 4. Because take half of 4, it becomes 2. Right, this one here, because it's 2 got that, it's going to be exactly a 2. Because if you divide 2 by 2, you get a 1, and the rest are zeros, like this. Okay, plus, let's deal with the t right now. Right, the t also is minus t over 3 there, so we can take out the t out of 3. The t out of 3, which is exactly, okay, if you take out t out of 3, then you get what? You get something here. Let me see what we have here exactly, because this is exactly 2 that we got. Right, so yeah, there are too many. So now at this point here, you can get what? You get a 6. Right, you get a 6. Because if you divide 6 by 3, you get a 2. Okay, that's fine. And then here you have a 0, 0, you have a minus 1, and here you have exactly a 3. Right, so let us check these carefully and see what we are able to have out of this. Because in the end, then, what did we do here? We actually got this, and this became exactly minus 4. How did you do that? We said row 1 minus row 3. Okay. This is a small typo. This is a small typo, because row 1 minus row 3 is going to be a minus 2 here. Okay, yeah, not a minus 4, it's going to be a minus 2. So that's just the typo there. I'm just trying to check here. So this one, yeah. So this one is going to be a minus 2. It's going to be a minus 2. And this one is going to be a 2. And this one is going to be a 2. And this one is going to, no. This one is going to be a 1. Okay, the 2, then you divide by the 2 here, it's going to be a 1. It's just going to be x5. Okay, I'm just trying to rectify just one entry, one coefficient. There's one coefficient that is fishy. So this one is going to be a 1. Okay, it's going to be a 1x5. And here it's going to be a 1. And here it's going to be exactly just a t. So that when you actually factor out the t out of 3, this one is going to be a 3. This one is going to be exactly a 3. Okay, now with this, then we are excited to say that we have the basis that we want. What is the basis that we want? Okay, we've already got the basis that we want. So now we have got the span, the spanning set. From the spanning set, these are the two vectors in the spanning set. Right, so the two vectors in the spanning set will give us a basis for the null space. So we're saying a basis for the null space is A is.
Oh yeah, we have those.
Right, so the basis for null space, then we take this one, which is -14200. And the other one is going to be 300 -13, like this. Okay, so yeah, this one will be a basis for the what? For the null space. Let us find therefore a basis for the column space. All right. The basis for the column space will be as follows. Right now, we are trying to find a basis for the column space, but for the column space, we just need to look at columns that have pivots. Right, so we have this one here, and so we also have this one here. Right, so because it has a pivot this, it has a pivot that, and then the next one is this one here. And so, or you can take one of these or that, but you can just take the first one. Okay, so there are three of them. So which means, therefore, a basis for the column space of A is given by the first one. 2 minus 402. 0 minus 1, 3 minus 1. Okay, these are like the first and the second. Then you have taken this one. Then you take that one there, which is exactly 3 minus 6, 3, 6. Okay, so yeah, we're good. So yeah, these sort of just as the basis for the one. For the column space, once again, one can take, for the second one, can take this one or that one, meaning you can also choose that. And you can decide to choose this, and you can decide to choose this as the second and the third one. Okay, so you have that kind of freedom, right? So the column space has been obtained as those columns that contain pivots, or those pivot columns. Let's look at the next question. Right, now looking at question 1, we're looking at the null space still. Okay, same one. Okay, is this one now? We're interested now in dealing with the matrix U. So the matrix U is a row echelon form of the matrix A. Right, we saw that, and you need not check this. Now, which of the following statements is true? Okay, now we need to do some multiple choice sort of question here. Right, we need to do some multiple choice sort of question. So we need to make the correct choice. The system AX equals B, which is the matrix equation, has a unique solution for all B in R4. The system AX equals B has infinitely many solutions for all B element of R4. The system AX equals B has no solution for some B element of R4. The system AX equals B has a unique solution for some B in R4. The system AX equals B has no solution for all B in R4. Okay, let us look at these here and see which one, and we need to give the number of the correct statement. What is the number of the correct statement here? Okay, so let us think about. I think it's okay. Okay, so yeah, we're saying which one of the following is true. Right, so if you look at the fact that it's AX equals B, it has already been reduced for us to this. So you take a vector. We saw that x1, x2, x3, x4, x5. Okay, which is the vector of the unknowns, and we said this one must be 4 of them. Okay, but now these ones can be anything. So it's B. Right, so B means that you can call them B1, B2, B3, B4. B1, B2, B3, B4. So these are like 4 B's in R4. Okay, with this now, you compare. And by comparison, you're able to see that the bottom one here is actually 0, and is a 0 row. Okay, but obviously this is for all B in R4. So for all B in R4, you can take this one to be 1, 1, 1, 1, doesn't matter. Or you can put it 1, 2, 3, 4,
Okay.
because it's for all of them. So I mean, you can vary these and see what happens. And I mean, check if these runs you run into trouble with the numbers. Okay, but the bottom one, which is 0, it's going to equal to 0 here. And so if you are to say for all B in R4, would see that they actually has no solution for some B in R4. No solution for some B in R4. Why? Because the bottom is going to say 0 equals 4, but this is false.
0 equals to 4,
Yeah.
which is false.
False. And that would mean, therefore, there is what? No solution for this choice of these. So we just choose this because it's for all. So in other words, there's no solution for some B. Yes, for some B. Because if you choose this to be zeros, all of them, there's going to be a solution. Okay, so it is therefore to say for some. So the correct option would have to be no solution there for some. Because as obviously you'd have chosen, you make a choice of these B that is going to yield some no solution case there. So we continue right now to do the next point. Right, so we look at the next question. Right, so the next question is as follows. Okay, now let A be this. Let A be this. Let A be this. Okay, find all the eigenvalues of A. All right, so yeah, we're good with this one. And obviously just practice together. Show this pretty straightforward. So to find the eigenvalues of A, then say A minus lambda I, and we find the determinant of this. Right, so, and that would mean 4 minus lambda along the main diagonal, minus 3 minus lambda, and minus 2 minus lambda. And now the rest remain the same. Okay, right, like so. Like so. So in the end, then you need to find the eigenvalues of A. You need to find the eigenvalues of A. Right, so to find the eigenvalues of A, then we just we compute this determinant, and we equate this determinant to 0. Right, so now it's easier to expand along the bottommost row, and now at this point, this is plus minus plus minus plus minus plus minus plus. Right, in which case, therefore, it's minus 2 minus lambda.
Yes.
Right, so we have this one here, and if we cover this bottom row and that one, because we just have only one to do, this and that, what you're gonna have? You're gonna have a plus here, and then this one, which is gonna be 4 minus lambda, 2 minus 3, then minus 3 minus lambda. Okay, so this is 0. Now, if we have minus 2 minus lambda, 4 minus
Isn't there a
lambda.
negative?
Please come again.
Isn't there a negative?
Negative where? I need to check.
Okay.
Okay, please, yeah, okay, because I'm seeing I've put the signs here like plus, minus, plus, so that I can sort of remember the signs. And here we have the minus plus. If it's minus here, then it's plus minus, etc. Okay, and then obviously we're seeing a plus here, so that with this one. Okay, so we're seeing a plus. Okay. And if you have the plus there, then I've put nothing. And then obviously if you put this and that, then you'll be left with these guys here. Only this minus, because the minus, So you have exactly this. Right. So in the end, they multiply this with that. 4 minus lambda multiplied by minus 3 minus lambda plus 6 equals 0. So that in the end, you have minus 2 minus lambda. So multiply 4 times minus 3.
Oh, yeah, makes sense.
It's minus 12.
Okay.
So this is
Oh, yeah,
minus,
multiplying
minus 4 lambda plus 3 lambda plus lambda squared plus 6.
Yeah, minus 7. Yes.
Okay, which is exactly lambda squared. Okay, so you're fine. And then okay, we're gonna check if there's an error. Obviously, we're gonna always check. So minus 12 plus 6 is actually minus 6 equals 0. Right? It looks
minus 6. Yes.
Yeah, it looks all right. Right, we have minus 2 minus lambda, and then this is lambda minus 3, lambda plus 2. Lambda equals minus 2. Lambda equals this, and lambda equals minus 2. Okay, so they sort of repeat. So there are 3 eigenvalues. Right, 3 eigenvalues, but now 2 are repeated. Very interesting case here. We're going to be actually watching very closely whether the matrix is diagonalizable or not. It might always be diagonalizable. It might be defective. Right, so find the eigenvalues of A. Right, hence the eigenvalues. Right, hence the eigenvalues of A are lambda equals 3, lambda equals minus 2, lambda equals minus 2. So we have these. We have these. Okay, so this is the answer. These are the eigenvalues of the matrix A. So we're good. Next, let's look at the next question. Right. So in the next question, we ask the question: is the matrix A invertible? Yes or no?
Yes.
Is A invertible?
Yes, from last time. Yes.
Okay. No,
Yes.
Yes, definitely. Obviously, we're able to see therefore that it is invertible. Yes, from last time. So we actually can be able to say yes, because we discussed it last time in terms of the nature of the eigenvalues. And the reason for that is to say that A is invertible. Right, so A is invertible because of the eigenvalues themselves. And it is invertible simply because 0 is not, right, is not an eigenvalue, is not an eigenvalue of A. Okay, because if ever it happens that 0 is an eigenvalue, then we know very well that the matrix itself is not invertible.
It's not invertible.
Yeah, so at this point, it is A is invertible. A is invertible. So now at this point, right, so we continue. We continue. So now let us look at part C. Right, if you know, let A with this, for each eigenvalue of A, find a basis for the corresponding eigenspace. Okay, let us deal with the first one, the easy one. For lambda equals 3, lambda equals 3 is easy because it's only 1. It has algebraic multiplicity 1. But the minus 2 has algebraic multiplicity 2 because you saw that we got lambda equals 3, lambda equals minus 2, lambda equals minus 2. So the minus 2 now is going to potentially produce 2 vectors, 2 eigenvectors. So now let's deal with this one. Lambda equals 3. Let's call it lambda 1. Right, so if we call this one lambda 1, we actually consider the following null space. So we consider the matrix 4 minus lambda minus 3 minus 3, 2 minus 3 minus lambda minus 1, 0, 0 minus 2 minus lambda. So in each case, you have x, y, z. 0, 0, 0. So that you have here, which is 1 minus 3 minus 3. 2 minus 6 minus 1, 0, 0 minus 5. Okay, good. And therefore, you'd have x, y, z. Okay, yeah. Normally, we need to get the null space of this matrix here. Null space of this one. Okay, good. From last time, we actually did a question like this. But now, we need to get the null space of this. Now, to get the null space of this, we need to perform row reduction, because now this is having repeated equations and things. So it's always best to perform row reduction. How do we therefore do the row reduction? So we do 1 minus 3 minus 3, then we do 2 minus 6 minus 1, 0, 0 minus 5. Okay, we can just take the matrix like this and row reduce it. So which means that you have row 2 minus 2, row 1. Right, so it's minus 2 plus 1, 0. Right, so and minus 2, this one is 0. This one is 5. And then here you'd have 0, 0 minus 5. Okay, so
then you add the last two.
Then we add the last two. Row 3 with row 2, for example, and yeah, we can call this one 1 out of 5, row 2. If you add the last two, well done, 0, 0, 0. Right, if we multiply this one by 1/5, we get 0, 0, 1. And then we just have one more job to do. Okay, because if this one is 1 minus 3 minus 3, right, this one is a pivot, so it really can work up here in producing a 0 here, so that we have row 1 plus 3 row 1, row 2, which is 1 minus 3, 0, 0, 0, 1, 0, 0, 0. Okay, so that in the end, then we have x1 minus 3x2 equals 0. And then we have x3 equals, okay, yeah, just calling them x3, etc. But yeah, same. I call them x, y, and z here, so we can really maintain that. So, right, so yeah, you can just maintain it. Doesn't really matter. I'm just finding myself calling them x1, x2, x3. But you can call them, I call them here x, y, and z. So which means x1 is 3x2, x2, x3 is 0. Okay, good. So in the end, it's x1, x2, x3. So it is 3x2 and x2, yeah, the x1 is 3x2. But x2 itself is x2. This is very, very important. So now we can then say, we can call it as, doesn't matter. Right, so x2, sometimes you can call it x2, but you can call it t. Right, so yeah, let's just call it x2 because it doesn't matter. And then the x3 now, okay, I know that in your material, they normally use the variables s and t, and I'm tempted to think that for purposes of consistency, let us use those parameters and then go and say x1 is 3t, x2 is t, and x3 is 0. x1 is 3t, x2 is t, and x3 is 0, which is 3, 1, 0. Okay, let's continue, please.
Okay.
Right. And then now, what is then the eigenspace? It is a 310. Right. So the eigenvalue, find the basis for the eigenspace. So and that would mean that our basis here would be the following. Right, the basis for lambda equals 3. Right. Right. The basis for the eigenspace, just write in full. Right. The basis for the eigenspace associated with lambda equals 3 is given by 310.
Yes.
Okay, good. Yeah, we saw the 310 here. Now the mission continues, and the mission is to deal with the other one. We're dealing right now with lambda 2 equals -2, but also lambda 3 equals -2. So these are equal eigenvalues, meaning that this eigenvalue has algebraic multiplicity. Right, it has algebraic multiplicity 2. So that in the end is 4 minus lambda 2, which is -3 minus lambda 0, 0 minus 2 minus lambda. So this is one is x, y, z. 0, 0, 0. Okay, now we have 4 minus into -2. 2 minus 3 minus into -2. 0, 0 minus 2 minus into -2. Right, we still have our x, y, z. Let's take a look. Okay, call them x, y, z. It's okay. Right, so now let's see what we need to get the null space of this matrix here, which is 4 plus 2, 6. Minus 3 minus 3. Right, then we have 2, and then this is -3 plus 2, which is a -1, -1, 0, 0, 0. And then this one here is x, y, z. And this is 0, 0, 0. Okay, so we're good. Now, with these mentioned, we then have the following. Okay, as said before, we need to row reduce these for simplicity so that we get the correct simplified eigenvectors. So in this, as it stands here, it is a lot of redundant things, and let us actually see what to do here with the row reduction process. But good luck, it's very nice and easy. The numbers themselves are very wonderful and divisible. So, right, for example, I mean, we can decide, we can take this matrix straight away. And if you take this matrix straight away, I know in your material, I think I saw them using an arrow here. Okay, so you can use an arrow as well. And put the row operations under the arrow or around the arrow. Yeah, I've seen that. Okay, right. So at this point, you can apply this one. You want this one to be exactly this. Okay, you want this to be 1. So what is the easiest way? Just multiply by 1 to 6. 1. Okay, it's gonna produce some fractions, but yeah. Right, so it's 1 minus 1/2 minus 1/2. 2 minus 1 minus 1. 0, 0, 0. Now, at this point, we have what? Row 3 minus 2, row 1. Okay, so you have 0 here. And then here you have 0, 0. 0, 0, 0. Which means that x1 is, okay. Call them X, Y, Z. Call the variables X, Y, Z. So you can call them, yeah. So now that's very, yeah, you see now this is very interesting. So you'd have X is equal to half Y, half Z. Y is Y, Z is Z. The Y, you can call it T, S. So the other way around, where the T and the S are real numbers. Okay, we're good. Meaning that let's also write them on the other side. So if we then say, we agree that our X is a half Y, a half Z. So yeah, we can just continue and simplify this. We called Y, what did we call Y? Y is called T and Z is called S. That's our choice. So we have half of each of these. So it's half T, half S. And we called Y T and Z S, which is X, Y, Z. X is a half T, half S. TS. Half T, T0. Okay, now we're dealing with the S, which is 1/2 S, 0 S. X, Y, Z. Which means it is 1, 2, 0. Half S, 1/2 S is going to be 1, 0, 2. Okay, let's check. Let's check this one. Yeah, that's correct.
Yes, that's correct.
Yeah, definitely. Hence the eigenspace. Right, hence the eigenspace associated with lambda equals -2 is 1, 2, 0, 1, 0, 2.
Isn't that the basis for the
eigenspace? Yes, it is it is most importantly basis for the corresponding eigenspace. Well done for realizing that. Yes, hence the basis. Right. So we can say hence A, because there are many bases. Right. So hence A basis for the eigenspace okay. So hence a basis. Yeah, hence the basis for the eigenspace associated with lambda equals -2 is this one. Once again, we're saying A basis because there are many. Another student can factor out T here and have like 1/2, 1, 0. Like half, 1, 0. And then a student can have, if factor out only S here, it's going to have like 1/2, 0, 1. So all those kinds of bases will be correct. So it depends on the factoring process, but in the end, then the bases themselves become sort of row equivalent to each other. Let us move to the next question. Right, so is the matrix A diagonalizable or not? Yes. Okay, the short answer would be yes, and obviously we give a reason for the answer. And a reason for the answer is that A has 3 linearly independent. Linearly independent. 3 linearly independent eigenvectors. 3 linearly independent eigenvectors. Okay, so that is exactly, okay. 3 linearly independent eigenvectors. So that is sort of the reason, because we found 3 linear independent eigenvectors, and this one is a 3 by 3 matrix. So if ever you have a 3 by 3 matrix or a 4 by 4, 4 by 4, you must find 4 linear independent eigenvectors. So automatically the eigenvectors are linearly independent. You don't even need to check that. But if you get 3 of them for a 3 by 3, it's okay. Once again, there are certain matrices that are said to be defective. Just on this note, defective matrices. What is a defective matrix? Well, a defective matrix is a matrix that does not have 3 linear independent eigenvectors, yet it's 3 by 3. Okay, you can find there are matrices that will have like 2 vectors, 2 eigenvectors. Okay, so if it's 3 by 3, then obviously the 2 eigenvectors will make the matrix not diagonalizable, but this one is diagonalizable, so we're good. Next question. Next question.
So the
Yes?
eigenvalues don't have to be distinct
Yeah,
for
that's
it to be
it.
diagonal.
Yeah, that's
Okay.
correct. The eigenvalues do not need to be distinct for it to be diagonalizable, a very important point. So they can always be the same. You can have all of them the same. Okay, because for a 3 by 3, you can have that each eigenvalue is 1 or 2 or 3. So if all of them are the same, then you would need 3 eigenvectors that automatically become linearly independent. But you see, for some matrices, it's 3 by 3, it's a 3 by 3 matrix, but you find that there are 2 eigenvectors. So because of that, the matrix is said to be what? It's said to be
Not
not
diagonal.
diagonalizable. Good. Right.
Yes.
We move to the next one. Move to the next one.
Okay.
So, right, let's see. Okay, let's look at part E. Part E of this one is a very interesting one. If A is diagonalizable, find an invertible matrix P in a diagonal matrix D that does this job. If it is not, find a basis B for R3 containing at least 2 eigenvectors of A. Obviously, we've already said that it's diagonalizable, so we need to find the matrix P. The matrix P would therefore consist of the eigenvectors. Now, associated with lambda equal lambda 1, we call lambda 1 equals 3, so we put them in some order. Minus 2 here, and this one equals minus 2. Okay, let's look at lambda 1 equals 3. Okay, let's look at lambda 1 equals 3. Right, so lambda 1 equals 3. Okay, yeah, this one. Right, so it is 310. Okay, we got the vector 310, so that's what we're going to put. So we're going to put 310. Right, so you're going to put 310 exactly. Right, so here we have 310. Next, we have the other one, minus 2. Okay, the other ones are 120, 102. 120, 102. One, 2, 0, 1, 0, 2. Okay, so this is the matrix P. And therefore, if this is the matrix P, then we are able to quickly write the corresponding diagonal matrix. And the diagonal matrix is going to have these the eigenvalues in the same order. So you're going to have 3 first, minus 2, then minus 2, 0, 0, 0, 0, 0, 0. Like this. Okay, so yeah, we're good. We're good. We find the two matrices because it said if A is diagonalizable, find an invertible matrix P. This is the invertible matrix P. It will always be invertible. Don't even need to check if the inverse exists. Right, and a diagonal matrix D, so here's the matrix D is diagonal. And now this matrix P is such that when you multiply like this, it's going to be, because this is sort of a principle for the diagonal matrices, for the matrices that are diagonalizable. So always, it will always be true, this equation. You can even check to take the inverse of this and multiply A by P, and then it will actually produce the D. So you don't need, but if not, then find the basis B for R3 containing at least 2 eigenvectors of A. Right, so yeah, but it's not the case there. Okay, we move on to the next question because it is diagonalizable, so the P exists. Let's proceed to the next point. Right, we're looking at inner product spaces now. Let's look at question 3 for 6 points, and we're saying for P of X in P2, put the inner product to be actually the integral. I realized that there was a bit more calculus in this exam of 2022, so they put some integrals, they put some derivatives, etc. Now, here is the integral. So they're defining the inner product, P of X with Q of X, and this is actually the integral from 0 to 1 of P of X, Q of X, dx. You may assume that this defines an inner product on P2. Okay, good. Okay, so what is the examiner trying to say here? He's saying you may assume that this defines an inner product on P2 so that there's no point to verify the properties of an inner product and to see if indeed this actually satisfies all the properties of an inner product. The examiner is the right. 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 So we continue. We continue. So now at this point, then you want to find, yeah, okay. So let P be this and Q be that. P of X. Okay, so P of X. So the P is X minus 2. The Q is 2X squared. So if you have P of X, okay, we'll continue. So in the end, then if you, yeah, okay, so you need to just find the inner product. So the P are given and the Q, P and Q are given, so you just need to find the integral of this. So the integral of this, now you multiply the X by the 2X squared, you get 2X cubed minus 4X squared dx, which is 2 over 4X to the 4th power. 4 over 3X cubed.
Yes.
Right, so now we have 2 over 4, 4 over 3, and then you cube this. Okay, and then now you can minus. Okay, we substitute 1, then you substitute 0, it's going to be 0 minus 0. So now this 2 over 4 is like 1/2 minus 4/3. This is exactly 6. So this is exactly 3 minus, it's exactly 3 minus 8. Well done. 8. Thank you. Right, which is exactly minus 5 and 6. Right, so yeah, that's exactly the correct answer. And so you can be able to actually, here with much confidence, say that hence the inner product of P of X, Q of X is actually equal to minus 5 out of what? Minus 5 out of 6. Okay, so yeah, that's fine. So we found the inner product. Let's proceed to the next question. Let's proceed to the next question.
Okay.
Right, so the next question is obviously very similar. Let's just take a look there at the next question. Right, so we have the next question. Okay, this guy is They said pretty much the same thing all the time. Okay, so this time
Yeah.
around, this time around, you need to find the length of the vector, the polynomial q. And so to find the length of this vector, you just do the same. So you need to remember that the length is actually the square root of qx. Okay?
Yes.
So that is the formula for the length. So you sort of repeat this one here. And now you then say, so in the end is 0 that, which means it is x minus 2, 2x, which is 2x squared. So in the end, then, okay, 0 to 1. Okay, no. There's more. Okay, it's QQ. See, I'm putting P there, so it must be QQ. Wondering, this thing looks like what I just did now. Okay, so it is QQ, and QQ here is going to be 2x squared, 2x squared. Right, so it's going to be 2x squared dx, which is 4x to the 4th power dx, which is the integral of this 4 out of 5 x to the 5th power 0 to 1, which is exactly 4 out of 5. Then we put 1 to the 5th power 0 to the 5th power. The square root of 4 out of 5. The square root of 4 square root of 5, which is 2 out of the square root of 5. So in other words, hence the length is 2 out of 5. Because it's length, you can even write units here. Right, so the length of this vector, so yeah, the length is 2 out of the square root of 5. Okay, this is square root in the bottom. So that's exactly what you have there. So yeah, okay, this exam you can just master them. You really can see, obviously, I mean, we shall be finishing both this one, 2022 and 2023, and then we shall tackle also the 2019 and other related things. Okay, because I've seen those. Right, now let's proceed to the next question. Right, so in the end, then, if you look at the for which value of b will this one be orthogonal to this?
Yeah,
so in other words, yeah, orthogonal means the inner product is 0. Right, so it means that R of x, f of x has 0 inner product. So now, obviously, for which value of b, so you just need the b there. So which means that at this point, this inner product is given by the integral. By the integral from 0 to 1, the r is actually x minus b. Okay, and then now you have the next thing, the q. Right, so orthogonal to q, and q is 2x squared. Right, and this one is dx. Okay, so in the end, we have 0 to 1, which is 2x cubed minus 2 bx squared. Like this, dx. Which means, therefore, it is 2 out of 4 x to the 4th power minus 2bx cubed out of 3, 0 to 1 equals 0. You put a 1 there, which is 2 out of 4, 1 to the 4th power, 2b out of 3, 1 cubed minus 0 equals 0. Okay, So which means that now 2 out of 4 is like 1/2, and this is the same as you can move this on the other side, giving 2 out of 3b. Cross multiply this guy. Right, so if you cross multiply this, okay, it's out of 3 here. If you cross multiply these, it's going to be exactly 3. So you can multiply this one by 3 out of 2. 1/2, you multiply this one by 3 out of 2. You multiply it by 2/3 b, which means b is actually the same as 3/4, 3 out of 4. Hence b is 3 out of 4. B is equal to 3 out of 4. Hence B is equal to 3 out of 4.
Okay, let me just do it. I don't know what I did wrong. I got
Okay.
1.
Oh, is it? Okay.
But,
Okay.
oh
Okay.
yeah, I saw.
Did you realize any error there?
Yeah, I saw my mistake.
All right.
Yeah, I saw
Excellent.
it.
That's excellent stuff. Okay, good. So let us proceed right now to the next question. As a matter of fact, and if we proceed right now to the next question, we actually obviously are able to obtain the following point. Right, so the following point will be as follows. Okay, now here is a matrix, a 2 by 2 matrix, and we let A be this 2 by 2 matrix and write A as a product of elementary matrices. There's one way of really looking at these and saying you have 1, 2, minus 3, 4 is the matrix A, and you have 1, 0, 0, 1, you augment it. And if you augment it with the identity matrix, what else are you able to achieve at the end of this? Right, so what you're able to achieve at the end of this, you're able to see row 2 plus 3, row 1. 1, 2, 1, 0, 0. All right, and then it's going to be 3 by 2, which is 6 plus 4, giving us a 10. And this one is going to be 3 and a 1, like this. Okay, so this is a sort of thing that you're going to be in a position to sort of achieve. Right, so we're able to see this kind of a transformation. With these then in mind, we have exactly this particular matrix here. And this matrix here can therefore be seen as follows. Right, you can be able to see that therefore the matrix A can be written as follows. You can actually you can write this as a product of 3 matrices. And one of the matrices is this matrix here. And this matrix here can actually be written as the 1, 0, 10. Now, you can actually put a 0 here, right, in this matrix. So if you put a 0 here in this matrix, in the place of the 2, right, so these 2, therefore, can actually be compensated as follows. If you write 1, 2, 0, 1. To compensate for the 2, you're going to just cross-check that one with multiplication. And then at this point, if you have this matrix here with the 1 minus 3, and you actually obviously put a 0 here and a 1. Right. I want us to check if it is necessarily correct as such. I want us to check if this is very, very correct. So if you multiply these last 2, or the first 2, let's multiply the first 2, multiply these by that, you get a 1. These by that, you get a 0. These by that, you get a minus 3. These by that, you get a 10. 1, 2, 0, 1.
Oh,
Okay, let's check this one. Multiply these by that, which is going to be a 1. These by that. Now, these 2 is going to be helpful. These 2 we've put here, we figured out from here. So it's going to be exactly 2 there. These by that, it's going to be exactly minus 3. And these by that, is going to actually be a -6 with a 10. It's going to be actually 4. Yeah. Okay. So indeed, then you can actually be rest assured that this matrix factorization using elementary matrices is actually the correct one there. But once again, obviously, I know that this is not a very technical topic, but we shall spend a bit more time on this and look at a bit more examples, I'm sure, even larger matrices. But yeah, but normally they put 2x2 matrices. Yeah, but after I'm sure that the 3x3 matrix can be brought, and if it ever is provided, it's very important that we diversify and look at even higher order matrices. The size 3, size 4 will do. Obviously, yeah, we call them matrices of order 3. What is the matrix of order 3, order 4? Yeah, even order 5. Yeah, but yeah, the order 5, I'm sure, is sort of thing, because the aim is not to you see, in question 1, they normally bring large matrices like 5 by something, 6 by something in that question 1. But the rest of the other things, they know that it's going to take a lot of time to analyze the larger matrices. So normally they bring small ones. And with the small ones, then you can be able to see exactly what to do there. So that is something that becomes extremely, extremely important. Okay, let us take a look at that and see what to do next. We look at the next question. Right, so this one is a standard question in terms of linear independence. Answer the following questions. In each case, show clearly how you arrived at your answer. Is this set linearly independent or not? Right, so okay, there are a couple of ways to do this. Some of the ways are very tedious and long, but some are way too short. So okay, now one way is to look at whether these matrices are such that one is the sum of the other, of other matrices. Okay. So for example, if you look at this particular matrix here, if you add these 3, okay, very, very careful observation. But yeah, but you see, there are many ways to do it. This is the easiest, I must indicate, the easiest way for this question. Okay. So if you add all these 3, let's add this one. 1, you add this entry, 1 plus 0 plus 1. You get a 2. Okay, you 2. Add 0 plus 1 plus 1, you get a 2. You add 0 plus 1 plus 0, you get a 1. You add this with this with this, you get a 0. So if you add these 3 matrices, you get that one. And that means it actually tells you that you have linear dependence. Okay, but yeah, there are many other ways to come along. So you have linear dependence. Okay, so you're going to look at another way to sort of do this. Then you have linear what? Linear dependence. Now, if this is the case, what then can we do? Okay, let us analyze this and then say, clearly because of this observation that this is a sum of this, okay, which sometimes can be tricky to see because, you don't have time to see. If you add this one, you get that. You add this, you get that. These things sometimes are mixed up in the set, right? So, but else is not linearly independent. It's not linearly independent. It's not linearly independent. The last matrix. The last matrix is the sum of the other 3 matrices. Okay, what else? of the other three matrices. What else is, yeah, okay, we shall get to another approach to this of the other three matrices. The last matrix is the sum of the other three matrices. But again, there are a couple of ways that you can see this. Other ways that you can see this. How else can you be able to see this? Because it's not the only way. Because there are other ways to see this. Okay, so we're going to use another method to practice. So alternatively, you can take there how many vectors? 1, 2, 3, 4 vectors. So let A, B, C, D be scalars. Okay, we take them to be members of R. Okay, because we're studying real vector spaces, be members of R. Let these be members of R. Then we can be able to write a linear relation. And we write A times the first one. Okay, this is sort of the standard way to test all the time. Okay, because sometimes it's not easy to see which one is the sum of which one. So at this point, because there are 4 of them, so you write like this. And then you have this. Okay, which means therefore, you have A plus C plus 2D equals 0. B plus C plus 2D equals 0. B plus D equals 0. Okay, now we're adding here. This one is A plus C plus 2D equals 0. Then you can come here and say this one is B plus C plus 2D equals 0. B plus D equals 0. Minus A plus C equals 0. Minus A plus C equals 0. Okay. Okay, now you take a look at these ones and see, you need to solve this with the scalars. And what then are you able to do here? Okay, see, tedious process, but now obviously it is possible to get the answer to this. Okay, because now you can then say 1, 0, 1, 2. Okay, B0 is coefficient 0. Now here we have 0, 1 for the second one, 0, 1, 1, 2, 0, 1, 0, 1, minus 1, 0, 1, 0. Okay, so in the end, then this is what you have.
So if we get a unique solution, then it means that it's linearly independent.
Yes, if you get a unique solution, then it's linearly independent. Yeah, but now if you don't, yeah, it will be linearly independent with a unique solution such that, because what solution we want? We want A equals B equals C equals D equals 0. We want all of them to be 0 for linear independence. Okay, so now we're just checking here, obviously. But now in the end, then we expect, according to this observation, we expect that it's not the case. But now, let's just practice a little bit to say row 4 plus row 1. Okay, if you say row 4 plus row 1 here, it's 0. And then this one is 0, and then this one is 2, and then this one is 2, and then this one is 0. And then here, this one is 1, 0, 1, 2. Okay, so with that in mind, now where this one is okay, 1, 2, 0. Row 3 minus row 2. 0, 0. Okay, yeah, this one, you multiply row 3 minus row 2. So you subtract here, you get a 0. Row 3 minus row 2, you get a minus 1 here. Sorry that this mixed up a little bit, these entries. Right, so but you get a minus 1 here. This is 2 minus 1. Right, so it's minus 1, 2. Okay, yeah, it's minus 1 there. And then row 3 minus row 2 here, it's going to be minus 1, 0. I mean, if you get all zeros for the AB, for these scalars, then it means we have linear independence. Okay, yeah. So, but yeah, this one has too many zeros, so it won't be too difficult to do. And then obviously at this point we get 1/2 here. Okay, very interesting. I want to see how consistent this is going to be with our observation of the sum. Right, so now at this point, we can multiply this one by -1, row 3. Row 1 plus row 3. Row 2 plus row 3. Let's check. 1, 0, 1, 2, 0. Okay, if you add row 2 and row 3, you add this one. 0 plus 0, you have 1, 0, 1, 0. You can multiply, it's 0, 0, 1, 1, 0. So here, this one you can write row 4 plus 2, row 3. Okay, with that, 0, 0, 0 minus 2, 0. So, okay, let's just write this one here. There's something I'm trying to see what's going to happen here. Okay, there's always a chance of human error here with too many entries like this. Okay, the top one is 10, 12, 0, if you like, something like that. 10, 12, 0. Yeah, but it's not a 12, it's a 1, 2. Right, so this one is 0, 1, 0, 1, 0. 0, 1, 0, 1, 0. Double 0, double 1, 0. And 3 zeros minus 2 and 0. Right, next thing. We have a 1 here. This is very interesting. Okay, there's something I'm trying to explore here. I want to see, but obviously we concluded that. But this is exactly minus 1/2 fourth row, 0, 0, 0, 1, 0. And then now we can say row 1 minus row 3, which is 1, 0, 1, no, 0. We're minusing row 3, which is the 1 here. And this one is going to be exactly a 1, 0. And this one, I want to see what the scalars are going to be. All right, so now this one here is 0. So 0, 0, 1, 1, 0. Okay, like this. And then right. Okay. You see, this is making a claim. I need to check this. Need to check if there's no, yeah, because 0, 0, 0, 1, 0. And then now you can do row 3 minus row 4, row 2 minus row 4, row 1 minus row 4. All of them will produce zeros. So, okay. Like this. Okay, I need to check this. But now if you check very carefully, if there's no error, I'm also gonna check this. I can use a software. Let me just use the software quickly.
Okay.
I'm just gonna use the software to row reduce this matrix. And okay, yeah, let me just use the software. It's something I want to see. Okay, yeah, because the last, I mean, I expect that it must not reduce completely to that form. That is the expectation. But now this,
Yes.
yeah, I don't expect it to reduce perfectly like this. So, but there's an entry somewhere that might have been, you know, not, but now maybe not written properly. But what I'm gonna do is, because I just need to check before we forward. I'm just gonna be brief. So I'm just gonna use a software to find the solution to this system, and then I'm gonna compare the solution by the software to our result. Just a second.
Okay.
Right, to our result. So, right, so let me use Symbol Lab. You forgive me for that. There's something I'm just trying to see. Okay, let me use eMath Help. There's something called eMath Help. It's a very good software. eMath Help,
Okay.
matrix reduction. Okay, and you can say eMath Help Gaussian down. Perfect. Something I'm trying to see quickly. Okay, because I'm trying to check our calculation here. Right, so our calculation then is going to be, what is the size of this matrix here? So the size of this matrix here is going to be 4, and then it's going to be let me see, 2, 2, 4, A, B, C, D. So you have 4 and then by 5. Let's check that one. So you have 4 by 5. Okay, so 1, 0. Okay, I'm entering that matrix here. I'm punching in that matrix. So it's 1, 0, 1. Okay, I already have the matrix there, and the D is 2, and this one is 0. And then this is 0. The B has a 1. The C a 1. The D a 2. And this one is 0. And then the B is 0, has 0, a 1, a 0, a 1, a 0. And then here you have the last one, which is actually a -1, 0, 1, 0, 0. So if 1, 0, 1, 2, 1, 0, 1, 2, 0. 0, 1, 1, 2, 0. 0, 1, 0, 1, 0. -1, 0, 1, 0, 0. Okay, good. And okay, this just to perform the row reduction. So yeah, perform row reduction in this matrix, the 1, 0, 1, 2. Just taking the matrix. Okay, I've taken the matrix from the other side. 1, 0, 0, 1, 0 minus 1, 0, 1, 0, 0. Okay, so now the matrix that's row reduced, obviously see it's actually of this form.
Yeah.
So yeah, so it
That
doesn't,
means it's,
yeah. So
yeah.
it means it's linearly dependent. Okay, so you're able to
Yes.
see, therefore, in the end, you were supposed to have a bottom there, a 0 row there. There's supposed to be a bottom 0 row.
Yeah.
Let me just check. So that's the thing. So, so there's a small typo.
Okay.
There's a small typo. I'm just right back. There's a small typo because, yeah, that's the thing. I was just checking that. So, yeah, let me just see quickly if we can be able to see where the error just occurred. So this is 1, 0, 1, 2. So this is fine. And then here, I'm just trying to see if you can be able to identify the error. Row 3 minus row 2. Yeah, so this is 0 minus 1 minus 1, 0. Okay, row 4 plus row 1, 0, 0, 2. Okay, there's the mistake here. There's supposed to be 2 here. Because if you add row 4 plus row 1, it's supposed to be 2 there. And yeah, this would be, okay, this we can't remove. Okay, just one sec.
Okay.
Right, so yeah, so I just identified I identified the error. Right, so the error is here right now. It is on the fact that we just overlooked something. Right, I need to remove this entry, this 0, because it has affected that. I'm sure, therefore, that wherever we use row 4 plus 2, row 3, even this one is going to be affected. And this one is going to be affected. This affected the bottom row. We're good. Now let us check what we get here if we use exactly that part. See what we have. Okay, good. Right, let's see now. We must be okay. Right, because I was saying that if you added row 4, when the minute you added row 4 and row 1, right, row 4 and row 1, there was supposed to be 2 here. Right, and then now you have row 4. Okay, so if there's a 2 there, there's a 2 there, there's a 2. So you have 2, 2. And then if you have 2, 2, you need to change this operation. And this operation is going to change because you still can put a 2, 2. 0, 1, 2, which is 0, 1, 0, 1, 0. Okay, 0, 0, 1, 1, 0. Okay, you can do half row 4, 0, 0, 1, 1, 0. Something like this. Okay, yeah, okay. But yeah, but you've already seen from the e-method program. So let me just proceed and just do the last matrix here. So that is going to be exactly this one, which is the 10, 12, 0, 1, 0, 1, 2, 0. So in the end, then you have 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0. 0, 0, 1, 1, 0. 0, 0, 1, 1, 0. Okay, let's check this one. Yeah, anyway, we pretty much are fine, understand?
Yes.
So, yeah, so this is going to be row 4 minus row 3. So 0, 0, 0, 0. So you're going to have a bottom 0. And then we saw that even on that calculator program, right, this is going to be 1, 1. And then you would have something of this particular nature there. Okay, let's see what. Right, I would think that 1, 0, 1, 0, 1, 0, 0. Okay, so we have this. Okay, so because of that, so in the end, then you have exactly these there. You have exactly these there. Okay, so that's sort of what we're getting. That's sort of what we're getting. I'm just checking there. That's sort of what we're getting. All right. So with this, what else are you able to get? Row 1, yeah. Okay, you forgive me. Row 1 minus row 3, just reducing. But yeah, but we already know the answer. Right, so row 1 minus row 3, so this is going to be 0, this is going to be 0, this is going to be 0, this is going to be 1. I wanted this matrix here. So that's 0, so that you have 0, 1, 0, 1, 0, and then you have 0, 0, 1, 1, 0. Yes. So this is a sort of matrix that you're going to get. But obviously, this means linear dependence.
Dependencies.
Right. Yes, it means linear dependence. And therefore, if linear dependence, then means that you need to remove the vector. Normally, we remove vectors from the end. Right. So it means linear dependence. So if it's linear dependence, okay, it means linear dependence. Okay, right. So is this linearly independent? No. Okay, so that is
No.
right. So yeah, definitely. So we take note of that. Okay, we continue. Yeah. We continue. Now we look at the next point. Just look at the next point. Right, looking at the next point, let me see. Right, you see, yeah, so it's, which means linear independence, since you actually, since not all the scalars are 0. You can write that. Since not all the scalars are 0. Since not all the scalars are 0. So since not all the scalars are equal to 0. Okay, yeah, we have that. Okay, now B part. Part B. Right, so is if it is, explain why it is. Or if it is not, find an equation. A, B, C, and D, that all matrices, okay, yeah, is the span of S equal to the whole vector space of 2 by 2 matrices? Okay. This is interesting. Right. So is a span of S. Okay, this is even problematic because the vector space of 2 by 2 matrices is of dimension 4. Okay, so this one is of dimension. So the dimension of, okay, we write like this. Dimension of M2 cross 2R is 4. Okay, why is it 4? It is 4 because of the fact that, so I mean, are these two vector spaces equal to each other? That is the question we're trying to answer here. Right, and we've already seen that this set here, the span of S has actually now reduces to 3 vectors in its basis. Now, if the basis itself is 3, it means that it is therefore very, very problematic. Right, so is the span of S equal to that? Right, once again, the examiner is saying, if it is, explain why it is. Or if it is not, find an equation in A, B, C, and D that all matrices in the span of S must satisfy. Okay, if it is not, because it is not, these two are not equal.
Why is it not?
Yeah, okay. The reason why it's not, it's based on the dimensions. Because two vector spaces that are equal, they must have the same dimension. So the dimension of the vector space, like in general, we say that the dimension of Mn by n of R. Okay, dimension, we can even here put M by, yeah, you can put N by N, or you can even put general matrices. Okay, you can have matrices that are P by Q in size. Okay, so as a consequence, the dimension of that must be PQ. So it's this, the product of these two numbers at the bottom here. But now at this point, it means therefore, if S is to be equal to the vector space of 2 by 2 matrices, it must have the same dimension 4. But the dimension is the number of vectors that are linearly independent vectors. So we realize that this other one is a faulty vector, meaning the dimension of S is 3 at most, 3 or less. Okay. So because it is 3 or less, because of this other vector that we're to remove, that is the sum of the other 3, it means therefore these are not equal to each other. So the claim that they're equal is not correct. So if it is, explain why it is. If it's not, find an equation in A, B, C, and D that all matrices A, B, C, and D in span of S must satisfy. So we continue to examine these in detail. And now we then look and say the following. Right, so we need to find that equation. And therefore, finding an equation in A, B, C, and D that all matrices like this in the span of S must satisfy. Okay, right. So let us look at these carefully together. There's basically an equation in the span of S that all matrices must satisfy. So what is then the meaning of this? Okay, let's look at the matrices like this. Right, so the matrices like these, every matrix like this, if you had to say all matrices like this in the span of S. Okay, if we take this matrix to be in the span of S, what does it mean if this matrix is in the span of S? It means, therefore, that this matrix can be written as a linear combination of these particular vectors. Right, so if this matrix can be written as a linear combination of these particular vectors, then what exactly is the equation that can do the task? Right, we proceed to examine that with much caution. We take this one, A, B, C, D. Okay, this is the matrix. If this matrix is in the span of S, what is the span of S? The span of S means that you can take this one, A, B, C, D. Right, so the span of S is right like that. Right, so if this is in the span of S, you can write it as a linear combination of this. So if you write the span, there are many ways to do this, the span of S. So the span of this, 1, 0, 0, minus 1. 0, 1, 1, 0. 1, 1, 0, 1. 2, 2, 1, 0. So in the end, then we have the span of S. Right, so the span of S would be the linear combinations. So associated with this, therefore, if we are to say, therefore, this one is in the span of S, it means, therefore, we can be able to write these as a linear combination of any of this. Right, so which means, therefore, if you take the A, B, C, D, you can find scalars such that in the end, then all these matrices must satisfy. So in the end, what would this mean for us? Right, so it would mean that you can take some scalars. Suppose you take A, 1, 0, 0, minus 1, B, 0, 1, 1, 0, C, 1, 1, 0, 1. Okay, then you can be able to derive an equation out of this. Right, and then you have D, which is the last one. Okay, now, if you can actually be in a position to then say, this linear combination of matrices in the span produces this matrix here. Okay, produces this matrix here. So in the end, then, you'll get a couple of equations. Let us examine that. So if you then say A, as in particular, we've already examined it in the in our first. So if you write A into this 0 minus 1, B into the second one, okay, because that's what span means, and then you can be able to get an equation out of this that all the matrices must satisfy. So you can obviously you actually be able to get a couple of equations. But now you have this linear combination because the span means that you can be able to write these matrices as a linear combination of this. And if this is the case, it must produce this particular matrix. And I must mention that in general, you can, strictly speaking, write here very general things like X, Y, Z, W. X, Y, Z, W. Okay, if you write this linear combination, it will produce another one, which is exactly this. Okay, and then out of this, then we attempt to find the rest of these as the linear combination of the A, B, C, and D. Okay, for example, okay, but obviously we've already done this and we got the reduction part of the thing. So you would write X for this one. Okay, we've already reduced it. I know that it's going to take a bit of time here. Okay, you have A. That is the first one. These, that, and that produces A. Then the next one is going to be the Y, Z, 2W equals B. And then you have the other one, minus X, Z, okay, yeah, it's minus X, Z, and there's nothing, equals D. And then what else is there? There is a Y. Please come again. Wait, what is it?
It's fine.
Okay,
no, it's fine.
Okay, I think I maybe I made a mistake. Okay, right. So, okay, if this is Y plus W, okay, because strictly speaking, this is the sort of presentation you're going to have in general. Okay.
Yeah.
And once you get this presentation, you can therefore be in a position to get the X, Y, and the Z. But now, obviously, we've already row reduced this matrix here. We just need to get the X, Y, and Z in terms of the A, B, C, and D. Right. And obviously, you see, the trick then is that at this point, what then you need to get would be an equation that is such that the A, the B, and the C will be manipulated, and they're going to be of the form. So yeah, this is what I want to say then. This would then imply that you'd get an equation that is A minus twice B plus twice C plus D equals 0. And this would be the equation that is going to appear here. Okay, there's an equation that, because now what we're having is exactly what we started with. Okay, now instead of the zeros here, we've put the A, B, C, and D. So the bottom row that must be, it is going to be actually the 0. It's going to actually consist of zeros entirely, right? But in this position, we expect the rest of this. Okay, I know that we can do that with enough energy. Right. So in the we have 0, 0, 0, depending on how many zeros you're gonna have there. Okay, depending on how many zeros you're gonna have, like 2 4 zeros, and then here you're gonna have that linear combination, which is just so in other words, every linear combination would have to the matrix as said already, such that all matrices like these in the span must satisfy. So you'd have that in this is going to appear here. A minus 2B plus 2C plus D. And then this is equal to 0. Okay, so which means 0 is the A minus 2B plus 2C plus D. Okay, so that is actually what you're going to achieve. That is what we're going to achieve. But obviously, I'm sure that is going to, we can do that with enough energy, because the thing is, we've already row reduced this before, and I know that it wasn't difficult for us to row reduce this, but we made an error and then we got back. Okay. So, but we can do it, and I feel that we can spend some minutes to do it. Maybe we can just do it, but you get the drift. Right, let's just do it just to make sure that we're happy, and this question can be done in a way that is more understandable and you can remember it, because it might just come this question, you know. And
Yes.
and now and it's very important that if we have done it, you would have a fair level of confidence in doing it. So now we're then saying, yeah, we're saying X, Y, Z. So that matrix therefore is going to be 1, 0, 1, 2. 1, 0, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. Minus 1, 0, 1. Minus 1, 0, 1. Minus 1, 0, 1, 0. Okay, I just want us to explore this quickly. And then now it's 0, 0, 1, 0, 1. 0, 1, 0, 1. And then now when I have here, or saying here, then you're going to have the rest of this. So we have A, B, D, doesn't matter. A, B, D, C. Right, A, B, D, C. Okay, we performed the row reduction of this, but now something important, we must make sure that we have the very, very correct matrix here. Let's see, it's going to be this. 1, 1, 2. You can check here. 1, third one is a 1, 2. Just to make sure we have the correct matrix, otherwise then everything is a mess. Right, so if you have 0, 1, 1, 2, it's correct for this one. And then this one is for the minus 1, 0, 1, 0 for D. 0, 1, 0, 1. Okay, yeah. Okay, yeah, good. So just practice. All right, doesn't matter. Row 3 plus row 1. Okay, I want to get a 0 here. That's going to be 1, 0, 1, 2. A. 0, 1, 1, 2, B. Okay, row 3 plus row 1, 0. 0. 2, 2. And then it's going to be A plus D.
Plus D.
Good. 0, 1, 0, 1, like this. Okay, so let us see what we're getting now. Okay, when you get to this point, you've got this matrix here, 1, 0, 1, 2. Okay, let's just squeeze another matrix here. And this is row 3 and row 1 we've got. Right, so we did here row 3 and row 1. I want us to put another matrix here. Okay, this one is a 1. And then this one here, what can we achieve here? Right, so obviously at this point, what we can achieve is we can even multiply these ones by 1/2. Also, if we multiply these ones by 1/2, all right, 1/2 row 3, forgive me, I just want to explore and see what is happening here. Right, right, so it's A over 2, D over 2. Okay, I mean, you can get equations here. Then, 0, 1, 0, 1, C. Okay. 0112B. 1012A. Okay, let's see. Now, all right, so this one, 1012A. Right, with 1012A. 0112B. 0112B. 0011. 0011. A over 2, D over 2. A over 2, D over 2. Okay, 0101. 0101. D. Is C or D? C. Good. Right. So let's get to this. Now, let's continue with this. Okay. What do we need now? We need a 0 here. And then we can then say row 4 minus row 2. 0, 0. Yeah. Minus 1. Okay, so yeah, I said we'll get a couple of equations here. Right, so those are the equations the examiner wants. Right, so you have row 4 minus row 2, so it's a 0 here, and this one it's a 0 here, this one is minus 1, this one is minus 1. And then it's row 4 minus row 2, then it's going to be C minus B. Okay, so the couple of equations the examiner wants, so you identify an equation that is going to work. A over 2, D over 2, and then we have 0, 1, 1, 2B, then you have 1, 0, 1, 2. Like this. Okay, you continue the row reduction until you get an equation that is going to be, because now these variables, you need the simplest of the equations here you're going to choose. Okay, now, if you check this one and this one, you can use. Okay, yeah, definitely. So I'm going to do this one here and put row 4 minus row 2 at the bottom, and I'm going to squeeze just one matrix here. Okay, we're going to squeeze one matrix here. And now we actually can be able to just hit one equation that is going to be nice and easy and with zeros and doesn't have complicated things. So if we do row 4 plus row 3, 0, 0, 0, 0. Okay, now we have these guys here. Very, very nice. I think we just have hit the nail on the head with the bottom one having zeros and being the nicest of the equations of all of them. So yeah, we add these ones. So which is A over 2, D over 2, C minus B. Okay, yeah. If you get this one, then it is 0, then the rest you don't care. Okay, right. So you have A over 2, D over 2, C, D equals 0. Because the other ones are complicated. They have the X, Y, and the Z as part of them. So, right. So this one is equal to 0, so it's nice. And then now you multiply it through by 2. It's A plus D, for instance, plus 2C. Okay, this is B. Okay, so watch out. This is C minus B. Right. So yeah, but I'm sure you sort of get the drift. Right. So which is A plus D, and then 2C, and then 2B equals 0. Something like this. Right. Yes, it is exactly what the examiner got. Right. So in the end, then you have A minus 2B plus 2C plus D. It's exactly what the examiner got in the memo. Right. So they got exactly this equation, which was the bottom one. Okay. So at this point, then you'd have that the others you don't care, but all the matrices, it is in the span. If it is in the span, then it can be a linear combination of that. What did we do here to get this answer? We then said if this one is also in the span, we can write this one as a linear combination of these. This question was quite lengthy and was given how many marks? Can't see the marks. Okay, question there is overall 10 points. So yeah, sometimes they're very mean when it comes to marks. Because I would imagine that this is a bit more effort to get to the answer.
Yeah.
It's a bit more effort. Okay, if it's a bit more effort, I'm thinking of the duration of the paper. It's 2 hours. Okay, so yeah, because matrices are nice and
short.
easy. Yeah, isn't it? Okay, good. But we're fine. We move on to the next one. Right. So I wanted us to sort of conclude this particular question. Right. So if you look at this particular question, now this one, write down a basis B for the span of S. Okay, here's the span of S. You need to write down a basis. So the basis is going to contain basically 3 of those. So yeah. So because we've already seen that this one is linearly independent because of this, therefore a basis would be okay. But also the basis you could pick it from the row reduced from the pivots. You can see which ones are which vectors are. So we pick the first 3. We pick the first 3. So if you pick the first 3, 1, 0, that. Okay, so yeah, this is the basis for the span of S, because this one is out of the picture, because it is a linear combination of the others. All right, so we move to the next point. Okay. Okay, now if you look at the part D, is this one. So is B a basis for MT2R? Well, we've already seen that because they're not equal. The basis it's of dimension 3. It has 3 things, and this M22 must have 4 vectors. So B is not, because any basis any basis must have 4 elements. The basis must be of the same dimension, or the vector spaces must be of the same dimension. So B is not. Is not a basis. Right, it's not a basis for M2 cross 2R. Okay, since, nice point. Since the dimension, okay, the examiner uses exactly the words we've been using. Since the dimension of the M2 cross 2R is 4. Okay, this one is dimension 4 because 2 by 2 is 4. And therefore, every basis for it must have 4 elements. Okay, it must have 4 elements. And now we can see that this basis is having 3 elements. For A, we take any matrix. So we can take any matrix, A, B, C, D, such that okay, so for A, you can take any matrix other than that equation we got, which is the A minus 2B plus 2C plus D, such that this equation is not 0. Okay, because if this equation is 0, then we have linear dependence. So we force it not to be 0. Right, and we can continue to then say, for instance, through guesswork. Right, for instance, you can have this matrix 1, 1, 170, such that you choose this number so that if you put the A, B, the C here, A, B, C, D, if you put these numbers here, it's not 0. Then that matrix this matrix with A, B, C, D, it's going to work. Right. So in this matrix, therefore, we can put it here in the set S, in the span. So if we put because now we can decide we discarded this matrix, then we can put this one. Okay, if you put this particular matrix here, then this is going to work. It's going to have 4 elements, etc. Yeah, obviously, we can go on to test that if these are linearly independent, if you form the linear combination, these will such that the linearly independent, and all the scalars you can choose here, 4 of them would all be 0. Okay, but yeah, it's just some algebra there. Okay, I think that for today it's very enough. But obviously we shall send you the recordings. I'm sure we'll start sending you the recordings so that you can start taking a look at some of the things we've discussed. But obviously, yeah, we are planning to go deeper into more of the algebraic techniques, but also a focus on the proofs as well. So that, yeah, you can be in a position to understand exactly what's happening and really get the most marks out of these. Yeah, it's a very interesting module. But once again, there's just an approach to these that makes things easy. So they don't appear to be very technical in terms of changing the structure of the questions. They appear to just be always, yeah, first question is same stuff, column space, null space, row space stuff, and so on. Okay, right. We must thank you for joining us. Right.
Thank you.
Yeah, we'll see you tomorrow. But obviously, we're planning to send you before, during the course of the morning, the recordings, so that you can just watch and see. Okay, but we thank you for joining us today. Right. Take care and have a good evening. Okay, thanks, dear, and goodbye.
Thank you.
Goodbye.
Bye.
Goodbye.